Good. Today will be more about chemistry and alchemy and all that. But I'll start with this super brief review of a backprop. So if you did not retain too much from last time, then consider this. So a single summation unit here with two inputs, and then I'm even omitting the activation function which goes out. Huh? So I could represent this in more detail as having some input come from the previous layer. I just call this Z1, and then having some multiplier. The indices here I'm giving are purely random, W1, and we multiply these two things, and then we have a second input, Z2, which we multiply with a weight, W2, and we have a product between them, and then we sum them up, and on it goes. And this produces some output. And if now in the process of backpropagation I learn that whatever comes out here should have been larger, then this information here, is sent along the summation towards the summation unit, and then we have something that's sometimes called a fan out. So the information, if the sum was too small, then that is the fault of both the summons. So the information is sent both ways, and this is why I'm writing here fan out. And then, if the product was too small, now it depends on the sign. If both Z1 and W1 were of positive sign, then we get the information that both, actually this weight should have been larger, and the output from the previous layer, Z1, should also have been larger, and so on. Okay, so this is the pattern that we have in this flow of information in backprop. And you can match this up with the formula and see that the summation formula and the chain rule gives you exactly this. Yeah? Okay, I want to start today by pointing out the many design choices that we have. And only one of them is architecture. And I want to talk today mostly about this one design choice, architecture. Yeah? But if you look at this formula here written in black, I have written up the training as an energy minimization problem. So we have an energy that is a function of the parameters theta, and we want to find those parameters theta that make this this energy as small as possible, where energy measures the discrepancy between our predictions and the ground truth on the training set. This energy also depends on the training set. This is usually left out or not written down explicitly because we just have one training set, and so people don't bother to write it down. But the influence is there, and one consequence is that we can try and augment this training set if we find it to be too small. Then we have a summation over all our points in the training set. Let's say we have capital N points in our training set, and then we measure the loss between the output that should be true according to the ground truth, yi, and we compare it with our prediction. And the prediction here, I've just called it, instead of a function, I've here written neural network, which depends on the input, on the features for the ith sample, and on the parameters. And finally, if we did only minimize this empirical loss, then we may be at risk of overfitting. And this is why people often use a regularizer in addition, that somehow biases extreme settings for the parameter values. So for example, we don't want these values theta to go through the ceiling. We don't want them to be super large. And this can be something as simple as, for example, here, just the Euclidean norm of the set of parameters. Okay, now, essentially each of these terms in the equation encapsulates a design choice. Yeah? So going from left to right, it's easy to write argmin, but in fact, we here have a nonlinear optimization problem in 100 million dimensions. Yeah? So there are quite a few things to say about this initialization, about this optimization. And we will devote next week to it when we discuss natural gradient descent and connections to information geometry. But beyond the actual optimization algorithm, there's also the question of how do you initialize your parameters and many others. Then I mentioned this dependence on the training set, which can be augmented artificially by either distorting the samples that you have or by simulating more training data. More on this in a few minutes. Then we have the loss function. In the easiest case, if it's a regression that we're trying to do, then usually we use the L2 loss. If we're trying to do classification, then we'll use cross entropy or logistic loss. But if we don't just want to predict a single number or a single category, if we are trying to predict something like a segmentation, then it may make sense to use a structured loss function. And some of these can be made to be differentiable. Sometimes it is not meaningful to accumulate a pixel-wise loss. So for example, a problem of current interest is to extrapolate a video into the future. So given 20 frames, speculate about what a possible future could look like. And we have ground truth because we may know what the video really looked like. Yeah? And we're trying to predict the frames that we now pretend we don't know. And in such a case, it doesn't make sense to use a pixel-wise loss because, for example, if we see if we are looking at a human walking, what matters is that the person continues with the correct gait. It does not matter if we put a foot a millimeter too far in front or not. Yeah? So pixel-wise loss is not sensible, and a very interesting recent approach, which I think we'll discuss in more detail because it's relevant, is adversarial loss functions. Then there is the architecture, and then there is the question of the regularizer. Now, briefly about the training set, I will show you today architectures with easily 100 million parameters, and of course you need, matching amounts of training data to find meaningful values for so many parameters. And if we have too little training data, well, we can either reduce the number of parameters or reduce number of effective parameters, which is connected with this discussion about architecture, or we can try and somehow artificially inflate the training data. So I've written here, emulate more training data. And with this sketch, I want to point out that image transformations which are completely trivial to us are not trivial if you simply vectorize the image and take that as feature vector. So here, for example, I have two images. As a human, we even need to look twice to find out what exactly is the difference. The difference is, in this case, a small translation. So the camera was rotated a little bit. And, well, if I now asked somebody to interpolate between these two images, then you would probably produce an image, well, that looks the same, but with a little bit less of the shift. But, if we do this just purely geometrically, we say each image is vectorized, and that is my feature vector, then I have a point 1 in feature space for the first image, I have a point 2 for the second image in feature space, and if I now interpolate linearly between these 2 points, then I get the result on the right, which to a human does not look meaningful, but to the machine that's a completely legit operation on two feature vectors here. So what I want to point out is that, for example, this trivial act of moving an image a little bit, which to us humans we don't even notice it if an image has been shifted a little bit or not, in this space of vectorized images, this corresponds to an extremely nonlinear trajectory, which is the thing that I try to show here in green. And then the image that is moved halfway between these actually sits somewhere on this trajectory or in this manifold if you have more than one parameter. Yeah? So I wrote here image transformations that are trivial to us correspond to non-trivial trajectories in pixel space. And if we now want to let a net imitate or acquire a little bit of this animal robustness of perception, then we can try and train the network to become invariant or equivariant to certain transformations. And I've listed a few here. For example, we could present the same image, let's say in an image classification task, but we rotate the image a little bit left and a little bit to the right. So this means that in feature space, my original image, let's say, is here at this position. And then by rotating my image a little bit, I start to map out a small part of a nonlinear trajectory. So rotating an image, again, it's some complex trajectory in this feature space. I only know that it's a closed trajectory because if I rotate the image through 360 degrees, I come back out at the starting point. Yeah? And by rotating my image a little bit, I trace out the beginning of this nonlinear trajectory. And then I can say that at each point along this trajectory, the label is the same. Yeah? For example, the image label could be castle, and now I can inflate my training set and say, you know, these points are also castles, just a little bit rotated. And we can do the same for scale, we can do the same for translation, or we can do the same for images that have been elastically deformed. Sometimes it makes sense to mirror images, to mirror them left-right, and so on. And all of this is called data augmentation, just a poor man's way to augment the amount of training data. Then there's also a more beautiful way, namely to code these invariances explicitly into the structure of the network. And this is possible or has been demonstrated only for very limited transformations so far. Specifically, there's quite a bit of work going on how to do this for a rotation. And if I may self-advertise a little bit, so when I gave this lecture before, I made a suggestion on how to do it. And then somebody did this in a master's thesis, Maurice Weiler, and he came up with a very nice algorithm, and he's now submitted it, and let's see if this gets published. Okay, so those are some of the, I've mentioned some of the many design choices in neural networks. And today let's talk about architecture. In computer vision, the neural networks that are really being used are convolutional neural networks. And I want to explain why they are so popular. In my example here, I pretend that on the left-hand side, I have just a scalar, a gray value input image. And well, I have, let's say, 1,000,000 pixels. And now I could have in my first layer of the neural network 1,000,000 perceptrons. And if I could draw very, if I was very good at drawing tiny things, then I could draw one of these perceptrons, and I could connect this perceptron to each and every pixel in the input layer. And let's say for semantic segmentation, where I want to predict one class per pixel, I would have to associate it. I would have to associate one perceptron with each and every, well, position in this first layer. So for 1,000,000 input pixels, I would have 1,000,000 perceptrons, and each perceptron, if I impose no kind of symmetry or anything, each of these perceptrons would have 1,000,000 weights. So I have 1,000,000 perceptrons with 1,000,000 weights. That is 10 to the 12 parameters and more than you want to store or learn or so. Yeah? Because this is just a single layer neural network. It's nothing fancy yet. So too many parameters. So we somehow need to break this down and make it simpler. Instead of using a fully connected layer as just proposed, it is possible to use locally connected layers. So here's an example where the red perceptron only receives input from 9 pixels in the previous image, and the black perceptron receives input from only 9 pixels in the previous image. So we have strong localization. In this case, the number of parameters would just be 9 million, because of 1 million perceptrons, 9 parameter per perceptron. That starts to be useful. However, if I want to build deep networks, that is still too much. And also in images, translation invariance is something very desirable. So we can expect that it's useful, for example, to learn something like an edge detector for something that detects edges in the input image. And it is not very data efficient and not very compute time efficient to relearn what an edge detector is for every position in the image. An edge is an edge no matter where it is in the image. And this is why the idea of weight sharing has been introduced. Here I now have 2 distinct sets of perceptrons or filters. I have a layer with these black perceptrons, and all black perceptrons share the same weights. So they all receive input from a local image patch, but the weights for all perceptrons in the black layer are identical. That means if we leave aside the activation function, then this would be a linear shift invariant operation, and linear shift invariant operations can be implemented by convolution, hence convolutional layer. And in this case here, okay, we have the black perceptrons with one set of weights, and then we have the green perceptrons with another set of weights, and then we can do this multiple times. So a typical number would be to have, for example, let's say 64 layers of perceptrons, but each of these layers has only a tiny number of parameters. Yeah? So for example, only 9 parameters for each layer if I use these 3x3 filters. So that still is quite, a lot of computation to do, and this is why graphics cards are needed. But each of these computations is extremely primitive. It's very simple, so this is why it maps to graphics cards so well. And this starts to become data efficient because we have so few parameters per convolutional layer. Now, how to sketch these things? Here, I have somehow shown them stacked side by side. I could also show them stacked one above the other. One above the other is not so useful when I want to have 64 of these. So a typical way of plotting this would be to say that we have here a 3D box where on this side of the box, these are just the dimension of the input image, and then the box would have a length of, for example, 64 to accommodate these 64 filter outputs, which I can look in terms of, so I can look at them as pictures. I would get 64 intermediate pictures for every input image. Okay, and then we could sketch a network like this. So for example, I have just a scalar input image, and then this from the scalar input image I extract many features. This is the linear operation. Then I use a nonlinearity, for example, a rectifying linear unit, which just sets negative entries to 0 and leaves the positive entries as R. Then I would apply another linear operation, perhaps with many more distinct filters. Then I get this representation here. Another nonlinear activation function, and so on and so on. And in the end, for example, if I want to do just foreground, background semantic segmentation, if it's just 2 classes, then effectively I just need a single output layer, namely the probability of each pixel to be foreground, let's say. So just a number between 0 and 1 for every pixel. If I want to write it as a nested formula to connect to what we said about backpropagation and so on, then you see here this is a nested set of functions. The very last function in a classification setting is the softmax, which normalizes the outputs and makes sure that I get a proper probabilistic output for each pixel or each image. And then this takes as input a linear transformation of the output of the previous layer. And the output of the previous layer is a nonlinear activation function, here a rectifying linear unit applied to a linear transformation of the output from the previous layer, and so on and so on. So we have a deeply nested function here, which overall I can write as my neural network, which depends on the input x and parameters w. Okay, and the network that I've shown here would be the kind of architecture that is used for semantic segmentation, where the input is an image and the output is an image with capital K channels. If I have capital K distinct classes like pedestrian, sky, car, street, etc., that would be an example from the Cityscape benchmark. Another problem that has been studied, especially in the a few years back, was image classification, where an image is put in and then the output is a vector that tells me which out of the capital K classes are present in the image. So these need not be mutual exclusive. So for example, there can be both a horse and a rider in the image, and then I would like to see entries for horse and for rider in my output vector. And a big data set that was used to drive this bit of research has been ImageNet, which is a hierarchical data set. For example, we here see a hierarchy of a husky is an example of a working dog, is a subset of dogs, is a subset of the canines, and so on, all the way up to mammals. And so first, this existed as a hierarchy for natural language concepts and was later augmented with images. And in 2012, this was the first challenge which asked people to classify images into 1,000 classes, and there were 1 million training examples. And this was a big leap from the previous challenge, which had, I don't know if it was maybe 30 classes or 40 classes, and much fewer training images altogether. So this is the first time that neural networks really came to prominence. And image classification is by now mostly a solved problem. So people are looking into harder questions like instance segmentation. Yeah? So to delineate every instance, so not just say, yes, there is at least one dog in this image, but to delineate on a pixel by pixel basis which pixels belong to which dog, and so on. Yeah? That's a much more detailed question to ask. Okay, and now in the following, I want to use these two problems, image classification and semantic segmentation, as benchmark problems, and look with you at a couple of architectures that have been used to address these problems. I will also mention in two cases pose estimation where the input is an image and the output are key points. Such as, for example, head, left shoulder, left elbow, and so on, grouped by person, if there's more than one person in the image. And challenges, there's, for example, a post-track dataset by Jürgen Gall and others also. Okay, so these are our guiding problems when looking at architectures today. But before we go there, I want to give you the chance to ask questions if you have any. Yeah.
For the image you sent, we consider the 9 neighbors of the center pixels. Is it the same idea like the amount of random field? We only consider the the neighboring pixels?
So I would say yes, on a qualitative level, it is the same fundamental idea. There are, of course, also differences because the neural network, as last week I showed you this taxonomy of neural networks, so including probabilistic ones and deterministic ones, and the deterministic network is just a complicated nonlinear function of the inputs. So the probabilistic interpretation would not be the same, but the concept to have an operation acting on only a small local subset of entities, yes, that is very much the same. Yeah? And because you bring it up, an argument can be made that, for example, a single perceptron here, it looks at 3 by 3 pixels in the input image. But a single perceptron here, it looks, for example, at here a 3 by 3 volume of perceptrons from the previous layer, and each perceptron in the previous layer looks at 3 by 3 pixels, so that this pixel then effectively looks at, well, with boundary effects, what is it, 8 or something, pixels in the input image. So in other words, there is this notion of a receptive field. Which asks, for a given perceptron depends on which pixels in the input image. And this receptive field grows as we go deeper into the network. And things like that have also been modeled in, coming back to a question, in hierarchical Markov networks. There have also been empirical studies of the receptive field. So in principle, in a very deep network, the receptive field is large. It may even encompass, let's say, the entire input image. In practice, the receptive field, when you estimate empirically these contributions, is not quite as large as the theoretical receptive field. So what do I mean by that? Let's say the theoretical receptive field is maybe this size, and then the effective receptive field is maybe that size. So the effective receptive field is more localized than the theoretical. I don't remember the title of the paper, but there is one from the Otasun group which studies these effective receptive fields. More questions? Yeah?
So the intermediate pictures that one can generate from the blocks, do they correspond to the filters?
So you mean these images here?
Yeah.
They correspond to the outputs of those filters. Yeah? So the filters themselves are just these, let's say, 3 by 3 masks. And then these are, well, these intermediate representations. These are the outputs of our nonlinear filters. With the filters themselves, by the way, a big deal has been made in recent years about what is better, small filters or large filters. And for a long time, people have been using, for example, 3 by 3 filters. Yeah? So let's say this perceptron in the next layer would depend on these pixels in the previous layer. These days, it is more fashionable to use filters which have bigger gaps between their coefficients. So let's say for the same, use a different color. So for the same output perceptron, could I please have a different color? No? So let's consider the same output neurons. Then, for example, you can have you can use the same number of coefficients, but you could use, for example, these input pixels. So it's still just 9 inputs, but they don't come from a 3x3, but they come from a 5x5 window. And people who have learned classical signal processing, well, at least if I judge by myself, did not like the idea, because we subsample and we know from we violate Shannon's sampling theorem, and we don't feel, or I don't feel comfortable about it, and yet it just works better. So I think it's actually, from the signal processing point of view, a bad idea, but from the point of view of getting a lot of context for a limited number of parameters, it's apparently a good idea. And then maybe the strength of the good idea outweighs here the bad that you do in terms of the signal processing. Okay, more questions? Yeah.
Why you have a black layer and a green layer?
Okay.
And why you said that all the weights are the same?
Sure. So, one possibility would be the following. Let's say I have an input image, and I apply a linear filter, but now just a single linear filter. So I get a single intermediate layer, and then I use my rectifying linear unit to get a new representation. Now, for example, let's assume that this filter here performed an edge detection. Then let's say here originally, I had a black circle. What I have now here is just the outline of the circle, because I've detected the edge. And now I can process this further and do fancy things, but at this point here, I have lost the information if the circle is black inside or white inside. And maybe the task is in the image I have black circles and white circles, and it's very important to know what's the color inside. So I don't want to discard this information. So rather than just use a single filter, I am using several filters. Let's say I'm using W1 and W2. Let's say W2 is just a low pass filter. And now I have complementary information. Let's say my first filter captures these outlines, and the second filter strongly blurs. So in the second filter, only the big one survives, because the thin outline, the other one, it has been blurred away. And now I have a much richer representation of the image content. And now I can use both by taking a linear combination. So if I did show a single perceptron here, I would now take a linear combination of these two pictures. But because I don't want to deal with single perceptrons, I'm dealing with layers. So instead, let me do the following picture. I use a linear operation. I'm showing this with a tensor here, and then I get an output which now has 2 layers. And then I'm using the rectifying linear unit. I still have a representation with 2 channels, and now I can do something more interesting maybe. So now comes the next linear operation and so on. So this is the reason why, in general, I want to have more than just one feature per layer. And your other question was, why are the weights the same? It's just a design decision. It's me who says, for example, detecting edges is a useful thing to do, but there is no need to train a different kind of edge detection filter in the middle of the image or in the upper right corner. An edge detector is an edge detector. And so I simply require that all of these connections be identical. So let's say this perceptron here gets input from, so usually it would be at least 3 by 3, but here for sake of argument, let me say 2 by 2 pixels. And I just impose that these 4 weights be the same as those 4 weights, just to save parameters. Okay?
What you say is that you filter everything with the same filter. Yeah.
Yes,
For the first perceptron,
yes.
And the last
yes.
filter.
So, you know, this thing here, I could have, if my input image is called X and this first filter is called W1, I could have equivalently written this as a convolution of a spatial filter W1 with my input X. Yeah? And now I take this nonlinear activation function, so now I write small r for rectifying linear unit of W1 of X. And now I do something else. Yeah? So afterwards, I take another linear operation and so on. So yes, you're right, it's just a convolution.
Okay, can I add something?
Sure.
So the last thing we wrote with W1, 2,
Yes.
is a different notation to explain that we do these different filters in parallel.
This is
not up one after the other.
Yes, in parallel.
Of them in parallel.
Yes.
Like 64.
Yes, it's so you know previously I distinguished between W1 and W2, and now I just use creative notation to say it's same thing. A more systematic notation would have been to say, let's say W for weight. Let me put an index to say here we're talking about the first layer, and now the first feature map in the first layer, and then this would be down here would be then W12. And then this one I could simply have called W1, to say this is for whatever feature layer we have in there. This would have been more systematic. Yes?
Do you already put in the knowledge that it's an edge detector, or what parameters are learned?
Good question. So in practice, so today, no, I would not put in the information that I want to use an edge detector. I just train from scratch. A few years back, when hardware was not so powerful and so on, then you would not start with randomly initialized filters, but you would start, for example, with, let's say, the discrete cosine transform basis as filters, let's say. Use that as initialization and then do backpropagation. Today, we either start from scratch by initializing randomly and then training, or we start from a pre-trained network. So we take a network that somebody with a big GPU farm has trained on ImageNet, and then we use those parameters if the architecture is identical, or at least if the first layers are identical. And when dealing with natural images, then almost invariably we can of course plot the filters, or we can plot these intermediate activations that you mentioned. Almost invariably we see that the network does learn edge detectors and it does learn blob detectors and so on. Yeah, simply because this seems to be a very fundamental way of describing what's going on in an image locally. And these are also the same operations that are implemented in our retina. But it so happens that if you compare the performance of the entire network when using learned filters or when using nice hand-designed edge detectors, it turns out that the learned filters will work a little bit better in the end. Yeah? So this is for the early layers, and for the intermediate and later layers, it's very difficult to say what they are. So typically, so there is some research. People try to figure out, okay, in some, let's say, in some late layer here, deep in my network, I look at a given perceptron, and I ask, what does the input need to look like in order for this neuron to fire really brightly? So that's the kind of question that you could ask to reverse engineer, what is a given perceptron responsible for, or how does the network think? But there's not a single correct method to do that. And in particular, coming back to your question, if we look at the filters deep in the network, they usually don't really show easily interpretable structure.
Why do you always retrain the easy filters? Can't you just take the weights from a different network?
Yes, you can, and they may not change so terribly much. But if we now look at a neural network and where are the parameters in the network? So I was arguing that if we have small filters, like if we have 3x3 filters, and then maybe we have 64 features, then let's say we have less than 1,000 parameters here, and then later in the network we might have a fully connected layer. So let's say we might have in an image classification problem, we might have 4,096 features in one layer, and then 4,096 perceptrons in the next layer. And now each perceptron in the next layer depends on every output in the previous layer. So the number of weights we have here in such a fully connected layer would be 4,096 to the square. And this number is so much bigger than 1,000 that it doesn't really matter. So so I spend very little computational effort in doing backprop to the early layers. But when I do it, I find that my performance tends to increase a little bit. And so standard practice is to just train the whole thing, except in a small niche of literature where people do care about training neural networks on a small computational budget, and there you try to be as thrifty as possible. And there, this kind of argument may be made. So anyway, the first layers simply implement low-level filtering operations. There is maybe no need to fine-tune them for my application at hand, and I will leave them alone. Yes?
How are these, sorry, I think you said it before, but how are these first two layers combined again, right? Because if you have a second set, you don't have now 4 layers.
So, let's look at, here I said this is 2 layers. Let me draw them more explicitly. 1, 2, and now here is the next. Let me just do a single, so this is 3x3 by, let's say, 2. And here, let's just say this is a single layer, 3, or single feature map, 3x3 by 1. So now I have, this will be too many arrows. So now I have 9 pixels or outputs from this layer and 9 pixels from that layer or from that feature map in the same spatial position. And each of them will get its own multiplier, and all of them will be added up. Yeah? So in this case, if I have 2 feature maps in the previous layer, now I need to draw 18 arrows. Yeah? So each one has its own multiplier, and all of them get summed up here. Does that answer the question? Yeah. In the convolution step, not in the rectifying step. Excuse me, I was off in the network. Mm-hmm.
That is after the rectifying step.
Before or after. Yeah, so usually you have a rectifying step, and then linear operation, and then rectifying step, and so on. Yeah, excuse me. So in the rectifying step, you're completely right. I just showed this at the wrong position in the network. If I do rectification, the number of feature maps is not changed. Yes?
You said that mostly studying network from scratch is better results. Is then increasing computation power like the solution to every problem? Because computational power just increases with time. We can train any network from scratch and solve any problem.
Yes. So if computational cost is not a concern, so if you are a social media gigant, then it's always best to train from scratch. If you are a student trying to do your homework on a notebook, then you might not want to train a very deep network from scratch. So your answer is, can you just brute force the problem? The answer is yes. It works.
If you use such a pre-trained network, I guess you're always bound to its architecture, right? Because,
good question.
I need to input the weights of this network.
Yeah. Yes, good question. So, for example, let's say, okay, I'm now summarizing this and just plotting it as a rectangle, and input goes out here and output comes there. Maybe you have a network which was pre-trained in this fashion, but now you want the network to produce something else that is interesting. So, for example, let's say your input initially was just let's say your input used to be a single frame from a video and the output was a semantic segmentation of this frame. But now you simultaneously try and estimate the flow field, which is nice because you can do it in an unsupervised fashion. Yeah? So you can ask the network to always predict the optical flow between one frame and the next. And then you can compare it to what frame really did come next. And in this way, you force the network to also understand the way things are moving, which may help in turn the semantic segmentation task. And in this case, it's quite typical to share the first few layers of a network. So because we can say, okay, things like detecting edges and so on is needed for both branches, and it's just the later part that you want to be different. And then one possibility could be to use this part from the pre-trained network, or you could also use that entire pre-trained network and only initialize this part randomly. There's a lot of space for creative basteln here. But profoundly, yes, your question was, does the architecture need to match? And yes, of course, you can only copy, coefficients if at least there locally the architecture was the same. More questions? Okay, we've completely burned the break, but we've made good use of it, I think. So let's have a 10-minute break. And then we carry on with looking at some real architectures.